Hello. So the other day I ran across this pixel shader and I thought it created interesting patterns. And it also has the benefit of not having a lot of code. So I thought it would be a really good candidate for porting over to Niagara. And hopefully in the process we create something with a twist. Now, the idea I went with was, well, rather than having an array of pixels in our viewport, what if we mapped it to an array of cubes in space using our grid distribution? And the result of that is this color to space video. And if I pause it here, you can see the grid in the background. And our camera is positioned fairly high up, looking down on it. And the small extension that I did to this was I used the particle's color to drive the height of the particle as well. And that's why you get this tunnel-like effect with the cubes moving toward and away from the camera. So once I show you how to do this, hopefully ShaderToy can become a place where you can go and mine other shaders and use them to create, some kind of variation on a theme. Now to do that, we're going to start with a basic grid distribution here. There's nothing really in here. I've gone ahead and added a couple of particle update scripts that are completely empty, each one. And one of the first things we want to do is basically treat our grid of cubes here as a screen of pixels. And I want for each pixel each particle, I need to calculate a UV coordinate, in this 0 to 1 range. So we'll do that first. I'll just get rid of this map and replace it with this one. So this is our emitter properties, grid X, Y, and Z, which are defined up here in our emitter spawn here. So we've got a 10 by 10. And what we want to do on this side is, let's write out the particle. I want to write out a vector, a 2D vector. And it's going to represent our grid UV coordinate. So that's the result we want. And how do we get there? Well, it's very similar to some of our other tutorials and the math we've been doing. A couple of things. So Z is not going to be used here. It doesn't really matter. We just want X and Y. And the first thing I want to do is make a float out of this, because we're going to be doing some division, and we can't do integer division. So we'll do that. And we also need the execution index of the particle. Now, I think I have persistent IDs checked here. We don't need that. You could use it. Actually, no, we are going to use it. Sorry, because in my grid particle update script, I actually use persistent IDs, which I talked about in a previous video. So scrap that. We are going to add a particle ID here. Not that one. Take this and break it to get the actual index here. And then, so the math for this is we want to modulo this index by the number of columns here, grid X, and then we will divide it this as well, and pipe that into here. Now, at any stage, if when you think about this, you can work it out on paper with pencil, and then you can verify your results. This is something I do quite often. So after you output something here, you can use the attribute spreadsheet. You can play the timeline here, capture the result, and then filter the attributes here, and you can look at the results. Now we haven't set the y, but the x value. So you can see here we have 10 particles, and if we divvy it up in a 0 to 1 range, we get these fractional values that go from 0 to 1. So with 10 particles, we go 10% of the way there. So 0.2, 0.3, 0.4, all the way to 0.9, and then repeats again. So you can use this to verify that all of the results here are as expected. Okay. So that was for the along the x. Now the y is just slightly different. We want to take this again. Oops. Actually, I'll grab this one first. I want to take this and divide it, and then floor it before we divide it again. And again, I would encourage you, just, take an index. So this represents the execution index. So if you add a comment, say the execution index is 3, and then start working through this. So if you add comments along the way, that's something I do. I'll take 3 and I'll divide it by grid y, which is currently 10, and then floor it, and you see the numbers travel through the wires. It would be nice if Niagara had some kind of step functionality in the future, although that'd be pretty difficult to implement. Anyway, so this, I will just quickly verify it again in the attribute spreadsheet. Capture it. And as you can see, this is correct. So for these first set of particles here, along this row here, they move in a incremental, in tenths. And then they should all be along the zero row here, which is true. And then the next row would be all 0.1s and then 0.2s. So we've got this pattern going on. So those are our UV coordinates that we've assigned to each one of these particles. And then what we can do is we can use that information in our particle update script. So that's all there is to this. We can close that. Now, the hard part comes with porting this shader over. So let me just pull up the shader. So one of the nice things about Shader Toy here is you can actually change the code here. So one of the first things I like to do with any bit of code is, well, what if we reduce its complexity? So if I just do 1, it's only calculating, I can even comment it out altogether, the for loop, and we'll just set 1 value. It's the exact same. So we're only calculating the red channel, right? And that's one of the first things I did, is just kind of eliminate as much code as you can, or complexity, and try and get it down to the core, and then you can go back and then start on commenting things and bringing stuff back in, like these extra colors. And in the process, you kind of discover what the code does. So right there, it's calculating 3 different colors for this value of C, which is then written out to the fragment's color value. And then this P here, well, it's it subtracts a fraction here. So well, what if we uncommented that? And then you can run it again to see what it does. So you can see that P kind of positions it in the middle of the screen. So you could go and modify other things here. So you play with it, you get a feel for what the algorithm does, and then you can start porting it over. There's a couple defines up here. So Shader Toy has these variables that are passed into every shader, time, which would map to our emitter.age, and the resolution, which is our grid X and Y size. So, what to do next? Well, you can start implementing it using the nodes that come with Niagara, or you can take the shortcut and use a custom HLSL node. Now, another important thing to note is this is GLSL, OpenGL shading language. So there are going to be some differences, and we'll come across those. So for the custom HLSL, what we want to do here is kind of mirror the same inputs to the shader. So we're going to need, time and resolution here. And we can do that here by adding a little plus. The time will be a float. And if we right click it here, we can change this to T. I also want to add a vector 2. And this is going to be our frag coordinate, I think it was called. Let me just double check. Yeah, so our frag coordinate is passed as an input here into the function. Or sorry, that's right here. That one's frag color. So that'll be another input, and R as well was another one. Sorry. Up here we have our resolution, which again is our grid X and Y. Now, even before I did this, you can just kind of play with this custom HLSL node. You can create inputs and map an output. One of the first things I did was a simple modification of the color based on its UV, just to verify that my grid particle update script was working. Now, we already verified it in the attribute spreadsheet here, which is good. But if you wanted to verify it visually, what you could do is something like this. So if I create a node here, and I will also input T, and for this one, a vector 2D, we'll call it maybe UV for our grid UV. And let's output just a single float, and we'll call this C for color. Oops. I did enter on the keyboard for that. So let me quickly show you this. Sorry, a little sidetracking, but it'll be good. So one of the ways, again, we can verify our results visually is we should see a gradient pattern as the color values move from 0 to 1. So on this slide, what we want to do is make a linear color, and we'll just pipe in the same value, which is going to be a single float. If we plug it into the RGB, we're going to get a grayscale value, 1, and then we will output this to the particle color. And on this side, what we want to do is grab our particle vector 2D. We called it grid UV. Pipe that into the UV here. And we want to grab the emitter.age, and that's going to represent our time variable. And then for the actual code, actually we're not going to use time, we'll just map it directly to uv.x. Compile, apply, save, and we're not going to, well, we are going to see something because I actually set up the particle material here. So that was another point I wanted to stress is if you do the most basic thing, you'll verify that your workspace is set up and running. So the first time I did this, I didn't see anything because I didn't have the particle material set. The particle material is really basic. I don't even need this part. But it's just an opaque surface here, and it outputs the base color. So what we can do is once you assign that, then whenever you assign the particle.color, you can see the results. And we can see that it's working here. We have a gradation, a linear gradation from black to white. So 100% we're all set up and ready to go. So I'll just get rid of that and on to something more complex. So the code here. One of the things I like to do is kind of just add the code incrementally, step by step. You might be tempted to simply do a big copy and paste. I wouldn't do that. I would take it piecemeal, compiling it at every step of the way so you encounter errors as they go. But before we get there, let's create a vector here on this side. This will be our frag color. And here, what we're going to need is to grab our grid values. So I'll just grab emitter.gridx and emitter.gridy, both of which were floats. From that, we will make a 2D vector out of them. So grid y and x, if you remember, represents our iResolution.xy. And we can pump that into, which was then defined. So a define, if you don't know, is just a simple way to give an alias, or in this case it shortens the name. Instead of typing iResolution.xy, they just type R in the code below. So if I create an input here, a vector 2D, we will call this R. I'll just wire that in. Now whether we use it or not, doesn't really matter. We just kind of set everything up and get it ready to go. Emitter.age goes into the time variable, and the frag coordinate is our grid.uv. Now the output is going to be a vector representing the color. And what we need to then do, well, we can, I can break this vector, and then we can, like we did before, we can make a linear color out of it. Using x, y, and z, set an alpha of 1, and we pipe that into particle.color. Now, when this color variable comes out, another thing we want to do, and the reason I broke it out, is we want to basically use the color from any one of these components, and we're going to use it to drive the position of this particle in space. But we'll do that later, towards the end. You don't even have to do that at all if you don't want to. The first step would be just to get the shader up and running and working. Just double checking, see if I got anything else. I think we're good to go. So one of the first things here in the code, we will just grab it, is we'll just grab this first couple lines, copy, paste, zoom in so you can actually see that, and compile. And we got an error already. T, undeclared identifier. Why is that? That's weird. I do have T declared. It's right there. T. Time. Let's try that. Nope. Time undeclared. Weird. Emitter.age, wired into time float. Okay, let's try. See the problems I've already encountered? I got just declaring variables. Let's try a full rebuild. Nothing. VM compile failed. T undeclared. It's right there. What's going on? Okay, let's remove this pin entirely. Get rid of this. Get it into a working state. Yay, good to go. Okay, let's try adding it again. Float. It could be a bug. T. Emitter.age is also a float. T. Let's compile it. Compile. Apply. Good. Z is equal to T. Compile. Apply. And that time it worked. Strange. So, as is the case with usually everything you do in programming, and especially if you're on an experimental plugin or development branches, you got to do things in such small incremental steps. So these things don't trip you up along the way. Okay, so I'm very cautious. I'm very, what's the word I'm looking for? OCD about stuff like this. Okay, and that's, again, that's one of the reasons where you wouldn't just copy and paste an entire chunk of code. You almost have to take it line by line with this stuff. So we are good to go there. What's next? We're going to skip this for loop. And if you remember, I just commented it out. Actually, I'm going to go straight to the for loop because I already have the working code. But again, you know, the first time around, I did it without the for loop. And a quick note is that you can really only do for loops in custom HLSL. There is no for loop node for Niagara. So we'll grab that. Actually, I'll just grab this whole chunk here. And just delete everything between it. And I'm surprised it hasn't been complaining about this frag color yet. So the frag color is unassigned. So the frag color is going to be equal to C. It was C divided by L. Let's see if it complains about that. Good. So that was, let me just double check, C divided by L. And then he inserts this value of t here, which I don't think is even necessary. You can set that to 1 and it has no effect. So just C divided by L. Now the rest of this code here, oops, creates a vector as my tab is not working. Awesome. Delete that. So it creates a vector 2 and then another vec2 to represent p, which is then assigned the frag coordinate divided by r. Compile that. Error. Yay. New identifier, comma, or unexpected identifier. Oh, because I typed vect. There we go. Compile. Good. Next up, we did this. UV is equal to P. Sorry, maybe I'll minimize this here. It's hard to read sometimes. P. Great. So I'll grab this chunk now. And it's painstaking. It's weird. The tab doesn't work. It almost focuses something else. So UV is assigned the value there. Again, this P is used to position it in the middle of the screen. I will cover this later. Z here is used, is every frame, or sorry, not every time through this loop, it's used to adjust the value of Z. In Z, I believe, was assign the value of t. So it's kind of like time with a little increment to it. And then this vector, or sorry, this float of L, the vector p, calculate the length of that. So let's just double check this. Good. And we're almost there. And this is one of the reasons I chose a shader with very little code. I'll grab this. So you can spend quite a while you know, working through the algorithm of a particular shader and understanding it, and then translating it. So this is just a bunch of sign and multiplications. There should be nothing wrong with that. And this is going to be problematic, as you will soon see. So C, index of I, which is fine. 0.1 divided by the length, sure, absolute. And this is the problem right here. Mod. There is no equivalent of GLSL mod in HLSL. Now it's fmod, but that actually has a different implementation. And the reason I know that is because I had to look it up. So I went and looked at the documentation for mod, and it said this is computed as x minus y times the floor of x minus y. Now, if you look at the equivalent in HLSL, it's actually truncated. Why do I keep clicking that? So it's x minus y times the truncated value here. So it's a subtly different implementation, and it could lead to a different effect. You know, you can definitely try it out. But I was having problems earlier, and I couldn't figure out the problem here. So then, because we know the algorithm for mod, what you can do is just, you know, drop it in. So here I've created a new variable called m, and then just plugged in that formula, where x would be the UV and y would be 1.0. So it translates into that straight from the documentation, and then we can just replace this with the value of m. Compile that, and that's fine. So that was a little trip me up there. And then there's a couple of other things which I will talk about. But what you want to be doing now is just seeing what the results are here. So as you can tell, we actually have nothing. Let's do a full rebuild. And we have an error. Why do we have an error? That's one of the things I do not like about Niagara right now, is you compile something here, it compiles fine, and you go to your emitter and it doesn't work. And in this case, it doesn't really complain about anything. So what you can do is, if you clear your output log here and do a full rebuild, sometimes you can see that value here. So it says grid X was defined earlier, but its type is different. Int32 is not equal to float. Okay, so that's my bad. So these two properties here were not float. I was thinking of grid distribution X and grid distribution Y. So emitter, make new, int32. And one for grid Y. We'll wire those up. Compile, apply, save. Full rebuild. Yes, working. And nothing is on our screen. Hooray! Okay, so what's next here? What do we have? We have the particles color, but we actually haven't set the particle position, which would be kind of handy. Position on this side, and I'm going to add a particle position on this side. So again, we were going to do the height. Do I want to do that now? No, not right now. I'll just wire it straight through. Again, nothing. Tick it. Oh, there we go. Sometimes you have to tick the timeline, and a lot of the times you can kind of get lost in space, which is why I like to hit F on the keyboard to frame up the emitter. And you can see we got some action going on there. Not quite what we expected. Okay. So the reason for that now is this code here, or the original code, I should say, is doing some calculations to basically normalize the coordinates here. So if you play around with it, we don't really need to divide it by our resolution, because we've already normalized it here. And this we can get rid of as well. We don't need that. So if I do that, you can see it's positioned here, somewhat in the middle. We're missing that 1 pixel there, but because it's 10, you know, that's as close to the middle as it can get. And if we play it, we're starting to see patterns. which is really cool. So then what you can do is, once you have that on the screen, is, you can let's try increasing it. Let's do 50 by 50. Now it's all bunched together, overlapping. So then on your grid distribution, X and Y, you can move it, frame it up again. Maybe make it a little more square. Let's do 5,000 by 5,000. Nope, 6,000. Cool. So there you go, it's mostly working. Now, it's not going to be as painless as what I just showed you. It took me a while to realize that I needed to get rid of this value here, because it was already centered, or sorry, normalized. And you can alter other things. I don't think this is really necessary. Well, I don't know if that's true, to be honest. Let me try. Oops. Oh yeah. So it's fully gray now. Cool. So a little fractional value to get the variation in color. Yeah. Almost like a chromatic aberration with those red and green blue colors. Anyway, so the last thing to do is once you have it working, this thing is now we can play with it. So what I was talking about before is using the color to drive the height. So we can quickly add a couple of things here. One, under the module, we want to add a float. This can represent the height. And another thing is the speed. So we can affect the speed at which it moves up and down, because it's a bit erratic, as you'll see. So height will be, give it a default of 0, speed of 1. Let's just quickly hook up the speed, which would be the time here. So we want to take the speed and multiply it by the emitter age before we feed it into the value of time here. And if we crank this up, we can change the speed of the effect or slow it down. And finally, this position here, we will break this vector here and then make a vector. And we will wire X and Y straight in. And then adjust the value here. Let's just take the Z component and we will multiply this by the value of the height that we pass in before we wire it up into Z here. Oops, there we go. So as we adjust the height here, you should start to see them start to move up. Like I said, you might want to do something a little better. They seem the heights move rather far in a rather short amount of time. So maybe you could remap their range to get something a little more, you see, once I frame up on it, it's way down there. That means the heights are moving way up here. So if I set this to 0 and frame in on it again, and then just modify it slightly. And that's kind of why I position the camera straight down the center. This side angle is kind of cool, but I think the density of the particles needs to go up, because I don't really like how quickly some of these jump. I would like something more smooth like that. But that's something to explore in the future. You could also turn it upside down, look straight down at it, and then adjust the lighting on it, holding L on the keyboard, get something, and then try increasing the height maybe. And then of course changing the density of the particles. You could change the scaling of the particles, the rotation of it. You know, just have fun with it, work with it. Try porting a different shader toy. Anyway, that's it for now. Thank you for watching if you made it this far, and for those of you who support me on Patreon, thank you very much. And if you like my videos and want to see more tutorials, feel free to buy me a coffee on Patreon if you feel you're getting some value out of the tutorials. And thank you very much again. Thank you for watching. Bye-bye.